and we move on to a very, very crucial result of regarding the reduction of our functional to a reduced order reduced order Euler-Lagrange condition, right. So essentially we are going to talk about conservation laws, variational symmetry, and the famous Noether's theorem. Okay, so let me also, so the topic that I am going to introduce in this half of our discussion is all about Noether's theorem. So a little bit of a trivia. Noether was a German mathematician whose major contribution in mathematical physics was this Noether's theorem, which came in the early half of the 19th century and which connects the various symmetries of the problem into a reduced order equation known as the conservation law, which we are going to see in a very simple form in this topic of discussion. Okay, so now, so what is a conservation law? So let us consider a functional j of y, which is equal to integral from x0 to x1 f of x comma y prime to y of n dx, right. Let me call this as 1. So this is a functional with derivatives up to n order. Now suppose there exists a function phi of x comma y prime comma yn, right. There exists a function, let us say this derivative is up to kth order. Suppose there exists a function up to kth order such that d dx of phi, which is also equal to x comma y prime comma y kth derivative, this is equal to 0. Suppose we have a function whose the derivative is 0, then well, let me call this as 1 and this as 2, right. And so this is equal to 0 for all extremals y of j, right. So suppose we have a function whose derivative is shown equal to 0 for all the extremals y of the original functional j, then in 2 I see, so this relation is known as the kth order conservation law. 2 is called the kth order conservation law, okay, for j, kth order conservation law for j. Okay, so right, okay. So we have seen conservation laws in the past. Well, I will just quickly recall. Notice this function h is equal to y prime del f del y prime minus f. We have seen these conservation laws. This is the first order conservation laws. We have seen it in our Beltrami identity. This is the first order conservation law of the functional conservation law of the functional of the form jy, which is integral of x naught to x1 of f of y comma y prime dx, right. So this is my first order conservation law of this functional. We have seen that in our Beltrami setup. So then we can also replace, remember this is well, 2 is the case when we have only one independent variable. Suppose we have multiple independent variables. So what I am saying is, so for functions of several independent variables, right. Suppose we have t1, t2, tn, so on. Then 2, the function, the relation 2 is replaced by the result divergence of phi is equal to 0, right. So So, we see that for functions of several independent variable, the result 2 is replaced by divergence of phi is equal to 0, right. Okay. So, then so divergence of phi equal to 0. Okay. So, the Euler-Lagrange, remember, so what is the advantage of working out through all these conservation laws? Because suppose my k, the conservation law is a function, is a relation of up to functions of order k. Suppose k is n, is less than or equal to n, it can at most be equal to n. If it is less than or equal, it is less than n, then we have found a relation whose solution is also giving us the extremal y, but the relation is of reduced order, which means that we have to solve a lower order differential equation as compared to the Euler-Lagrange equation or a simpler equation. So, what have I said is the following. So, in general Euler-Lagrange equation for 1 is of order 2n, and if I have that k is less than 2n, then k is less than 2n, then 2, if k is less than 2n, then 2 is a lower order differential equation, for the extremals. It is a lower order differential equation for the extremals, which were extremals or the solution of the Euler-Lagrange equations, right. So, this is a lower order differential equation for the solutions for the extremals, which were the solutions of Euler-Lagrange equation, and that lies in this statement lies the power of conservation laws. Okay. So, let me just briefly mention what is, so once we have the what is the significance of Noether's theorem, we will introduce that a little bit later. So, Noether's theorem says that the links between Noether's theorem provides us the links between the conservation law and the so called invariance property of the functional, right. So, it links conservation law and links conservation law with the invariance properties of the functional, right. So, it basically tells that if you give me invariance properties, I can find out the conservation law. So, that is in gist the theorem, right. So, the key, which means that the key to finding conservation laws, lies in finding symmetries, right, or the invariance properties of the functional. So, right now in this topic of discussion, in this lecture, we will just assume that the symmetries exist or the invariance properties exist. We will show that, we will look at only those examples for which we know the invariance properties, and from there we are going to derive the conservation laws. In the next lecture, we will highlight a method of finding these symmetries. Okay. So, let us continue. So, symmetries. So, what are symmetries? So, symmetries are transformations under which the functional is invariant. Symmetries are transformation under which the functional is invariant. Okay. Okay, fine. Okay. So, let us look at the topic of variational symmetries. Now, what are variational symmetries? Let me introduce that. and how does it help our cause, that we will see. So, we consider again, we consider the functional, the simplest form of the functional to begin with. J of y is equal to integral from x0 to x1 of f of x y y prime dx, and let us now consider a one parameter family of transformation, right. So, consider a one parameter family of transformation, one parameter family of transformation, and let us call this the x component be theta of x y epsilon. So, my one parameter family is the parameter epsilon, and my y component is y of, well, I call this function as psi, which is a function of x, y and epsilon. So, my original coordinate axis is x, y. Let us talk about the problems in 2D, and my new coordinate axis is capital X, capital Y. And theta and psi represents the transformation from the original to the new coordinate system. Okay, where, so let me call this, so far we have numbered 1 and 2. So, let me call this this transformation function as 3, where theta and psi are smooth functions, of x, y, epsilon, right. And we also require the following constraint. We say that we put the constraint that theta of x, y 0, that is at epsilon 0, theta goes back to our identity transformation, right. So, psi of x, y 0 is equal to y, right. Or what I am saying is the following. So, this constraint means that at epsilon equal to 0 corresponds to the identity transformation. Okay. So, let us look at few transformations and let us see how does the functional behave under those particular set of transformations. Okay. So, consider this transformation. So, consider the translational transformations. Okay. So, we consider the functions of the form x is equal to x plus epsilon and y is equal to y, right. And I consider another set of transformation x is equal to x and y is equal to y plus epsilon, right. So, these, notice that each of these transforms correspond to the cases where we are translating one of the coordinate axes by epsilon. Okay. We can also consider another set of transformation also known as the rotational transformation. Let us say that the coordinates are capital X and capital Y given by x cos epsilon plus y sin epsilon and minus x cos epsilon plus y cos epsilon, right. So, these are my rotational transforms. We can check, well, then let me also introduce the concept of Jacobian, the Jacobian of transformation. The Jacobian of the transformation, which is given by partial x y. This is also equal to the matrix, well, the way we have described the transformation theta x, theta y, psi x, psi y, right. So, notice that this has determinant, delta of x comma y comma epsilon. This is also equal to theta x psi y minus theta y psi x, right. And well, we can see that the way we have described theta and psi, we can see that delta of x y 0 is 1, delta of x y 0 is 1, and also notice that the continuity of delta with respect to. So, what I am showing here is, notice that at one value of epsilon the determinant is 1. So, the determinant is non-singular for epsilon equal to 0, and if my functions theta and psi they are continuous, then we expect that in the neighborhood of epsilon equal to 0 the determinant is non-zero or the transformation is non-singular, right. So, what I am saying is the continuity of delta with respect to epsilon indicates that delta of x comma y comma epsilon is non-zero, right. So, this is non-zero for epsilon much less than 1 or close to 0, right. Okay. So, we call this setup, let me also call this set of arguments by denote it by A. So, I am going to refer these arguments later on when we will use in certain problems by A. Okay. So, then A means that our transformations are uniquely determined in the neighborhood of epsilon equal to 0. They are invertible because the determinant of the Jacobian is non-zero, which means that we can readily find the inverse, right, of the transformation. So, A implies that the transformations given by 3. Well, what is 3? That is what we began with. So, the transformation given by this 3. So, we are always going to refer to our most general form of transformation by our expression 3. Okay. So, the transformation 3 has a unique inverse, and which means that once we are given capital X y in the form of small x y, we can also write small x y in the form of capital X y. So, this is capital theta of x y epsilon, and this is y is equal to small psi of x y epsilon, right. Let me call this relation by 4. Okay. So, for example, let us recall our example of the translational invariance, the translational transformation, right. So, the inverse of the transformation that we stated here, look at this A and B, the inverse of the transformation we stated, inverse of A is given by, so in terms of small x and small y is x minus epsilon, and y is equal to capital Y, and the inverse of B is given by x equals x cos epsilon minus y sin epsilon, y is equal to x sin epsilon plus y cos epsilon, right. So, I can readily find the inverse. This was the inverse in the case of C, which was the rotational transformation we discussed. Okay. So, we can readily check that these are my results for the inverse, right. Now, further these two relation tells that, notice that we have two unknowns small x and small y in this inverse relation, and we have two equations, which means we can readily eliminate one of the unknowns, let us say x, right, and write down y as a function of capital X and epsilon. So, let me call this x. So, what I am saying is, from my inverse relation from 4 from 4 what I say is one can eliminate x and find y as a function of x and epsilon. One can eliminate x and find y as a function of x and epsilon. For example, if we go back to our case study of this inverse of A, so from A, let us do this exercise for example in A. So, I know that in my translational invariance case, small x is capital X minus epsilon and small y is capital Y of x, but x is capital X minus epsilon. So, this is small capital Y of x minus capital X minus epsilon, right. I call this function as y epsilon of x, right, y epsilon of x. Okay. So, this is my setup. So, that is what I just said. Now, again for C, we can repeat this exercise in C to see how we can eliminate one variable. So, in C, in my rotational example, rotational transformation case, let us assume, so assuming y of x is equal to x, I see that my x was given to be, let me write down the expression, x is x cos epsilon minus y sin epsilon, and this is set equal to y. So, this means that this is also equal to y and this is also equal to x sin epsilon plus y cos epsilon, right. So, x is this and y is this. Okay, fine. So, from here I can find y as a function of x. So, from here what I see that my y epsilon of x is cos epsilon minus sin epsilon divided by cos epsilon plus sin epsilon of x. Okay. Okay. So, then I also need to introduce some notation. So, the notation that I have is I also need to introduce the derivative of these new functions in this new coordinate system. So, the notation is y dot of epsilon of x. We see that this is d dx of y epsilon of x, right. So, this is my definition of y dot. Also, so from 4, from my inverse relation, I also need to find, from this relation I also want to find y prime of x or dy dx, where y is small y and x is small x. Okay. So, I need to find the derivative. So, from 4 I see that my dx is equal to theta x plus theta y, y dot epsilon of x, right. So, this is also equal to dx, and my dy is my transform, my is the following expression. This is psi x plus psi y times y dot epsilon of x, right, dy dx. Okay. Okay. So, from here what I see is that y prime of x is dy dx, y prime of x is dy dx. We can take the necessary, we can divide 2 by 1. This expression I see that this is also equal to psi x plus psi y, y epsilon dot of x divided by theta x plus theta y, theta y dot of epsilon of x, right. Okay. So, that is what we have for the relation for y prime of x. So, from here what we have, we are ready to describe the concept of variational symmetries after all this setup, after all this background. So, what are variational symmetries? Okay. Before even that, let me also introduce the concept of a functional being variationally invariant. So, what do I mean by that? The integrand, so the integrand f of x comma y prime of the functional, the integrand of the functional j in our original functional relation in 1. So, that is how I am numbering. So, if we go back, our 1 is this relation here, the functional, the setup of the functional, and the functional, suppose the integrand of the f of the functional j in 1 is called variationally invariant, over the relation, over the interval x0 to x1 under the transformation 3. So, it is variationally invariant under the transformation 3. So, here is the transformation that we, so again always I am going to refer 3 by my original set of transformation theta psi. Okay. So, this integrand is variationally invariant under this transformation 3 if for small value of the parameter epsilon in a subinterval AB, which is a subset of x0 x1, right. My integral of a to b of f of x y prime dx is integral of a epsilon to b epsilon of f of x y prime y epsilon dot of dx, right. So, which means that where, let me complete this statement, where a epsilon is the mapping theta evaluated at the starting point a times y of a comma epsilon, and my b epsilon is my psi of, well, not psi, but the same mapping, because we are trying to map our variable small x to capital X. So, theta of b comma y of b comma epsilon, right. So, that is my variable this. Okay. Okay. So, what have we got here? So, we are saying that suppose we are able to find a transformation given by 3, and under that transformation the integrand has the same form, whether it is in this coordinate system small x small y or capital X capital Y. If they have the same form over a subinterval, then the functional is variationally invariant, right. So, the integrand is variationally invariant. Okay. And then the second statement says that the transformation, if I see that the integrand is variationally invariant, then the transformation in that case, the transformation 3 is known as the variational symmetry. The transformation 3 is the variational symmetry of J. Okay. 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 So, what have we got here? Let us look at all these statements through some examples, then the idea will be clear. Okay. Okay. So, let us look at an example. So, let my x0 be 0 and x1 be 1, and f of x comma y prime is equal to y prime square plus y square, and we consider the transformation, x is equal to x plus epsilon and y is equal to y, that is this is our translational transformation, right. Okay. So, what we do is, from here I can find what is y epsilon. Y, we want to substitute y and we want to substitute y prime, right. So from here I can see that my small x is capital X minus epsilon and my small y is capital Y, right. And also from here I see that dx is capital Dx, and from here I see that dy is capital Dy, or this is also equal to y epsilon dot times dx, right. Or I see that dy dx, the derivative of y with respect to x, is y dot epsilon, right, y dot epsilon of x. Okay. So what we see is that the integral from a to b, y prime square plus y square of dx, this integral is also equal to, we plug in y prime, we plug in y, right. Now notice that the original interval was from a to b, right. When x was varying from a to b, if x was varying from a to b, capital X will vary from a plus epsilon to b plus epsilon. Using this relation, I see that capital X, capital dx, so capital X will vary from a plus epsilon to b plus epsilon, right. So in this interval, y epsilon dot, notice that once, let us see what is y prime. So y prime is y epsilon dot. So y prime, so y epsilon dot square plus y square. What is y square? Y square is capital Y square, right. So this dx is equal to this, and this is also equal to, so the functional form in this case is retained. So I see that this is of the same functional form, x comma y epsilon comma y epsilon dot dx a plus epsilon to b plus epsilon, right. So what I have shown here is that for this sort of transformation or the translational transformation, my functional is, my integrand of this functional is variationally invariant or has the same form to begin with, right. And which means that the transformation A, so A is my variational symmetry, A is my variational symmetry in this case. So that is the transformation I am after. Okay. Let us look at the same variational symmetry for another integrand. Okay. So let us continue looking at few examples more. So the example I have is the following. So example 2. So let again we set up x0 is 0, x1 is 1 and f of x y y prime. This is also equal to now y prime square plus y square x. So now my integrand is this. So again we use again the same translational transformation. X is capital X plus epsilon and y is equal to capital Y, right. Yeah. So from here we see that for this sort of transformation, we see that y prime square plus y square, when we plug, well, what have we got? Are we correct? Well, x will be x minus epsilon, again the same translation and transformation. So if we plug all these, so y prime square plus y square x will give us y dot epsilon square plus x minus epsilon times y epsilon square, and this is also equal to the same function. Notice, let me write it down like this. This is also equal to y dot square plus x y epsilon square minus epsilon y epsilon square, right. Notice that this is of the form f of x y epsilon dot minus epsilon y epsilon square, right. Okay. So what is the conclusion of this example through this example? The conclusion is that A is not the variational symmetry because the integrand is not variationally invariant for A, right. So which means that this is not, so this, of course this is not equal to f of x y epsilon comma y epsilon dot. So this is not a variational symmetry for j which is the integral of f, right. Okay. So, this gives us some perspective as to how to find variation, to check whether a transformation is a variational symmetry or not. Now, in general, students should be it should be mentioned that students should check that the transformation of the type capital X is equal to x plus epsilon and capital Y is equal to small y. This sort of a transformation is a variational symmetry. This sort of a transformation is a variational symmetry for j given by this integral f of y comma y prime dx, right. Well, right. So, this sort of a transformation is a variational symmetry where we have a integrand which is independent of x. So, this sort of a translational transformation will work. On the other hand, suppose we have a translational transformation of the form x is equal to small x and y is equal to y plus epsilon, right, and then we see that this is a variational symmetry for j which is given by the functional of this form where the integrand is of this form. So, we can check this is a general result for integrals of these two categories. Okay.